Hello, Calculus and Vectors class. Welcome to 5.5, Curve Sketching with Rational Functions. Here's where the rubber really meets the road. We are going to take all the skills that we built from 5.1 to 5.4, and well, essentially from Unit 4 as well, and we're going to put them all together in our curve sketching for rational functions. So let's start with this function f of x equals 5x over x squared plus 1. So let's start with the asymptotes. So let's start with the vertical asymptote. We know how to do this already. We just set the denominator equal to 0, and that's going to be 0 equals x squared plus 1. So in this case, it's negative 1 equals x squared, or x equals positive or negative square root of negative 1. And we know negative 1 doesn't give us a real number. So in this case, we actually have no vertical asymptote. So no vertical asymptote for this rational function. Next, let's talk about horizontal or oblique asymptotes. So first of all, before I do anything, let's look at the degrees of this. So it is a linear, it's a degree 1 over a degree 2. So in this case, we know that it can't be oblique because it has to be, the numerator has to be 1 degree higher. So we know we might have a horizontal. So what we're going to do is we're going to take that trick where we divide by the highest degree of x in the denominator. So let's take this. So we're going to find the limit as x approaches positive or negative infinity of this function. And we're just going to take that same thing, but this time, like we said, we're going to just look in the denominator, and we see that we have an x squared there. So that's going to be what we divide everything by. So we're going to take 5x over x squared divided by x squared over x squared plus 1 over x squared. So now let's do some canceling. So that's going to be 5 over x squared divided by x squared divided by x squared is going to be 1, and then 1 plus x squared. So now let's look term by term. 5 over x squared. If x is approaching infinity, it's going to be a very, very large number. So at the top, that's going to look, it's going to get closer and closer to 0. Then we're going to have 1, and then we're going to have another 0. So that works out to 0 over 1, or 0. So in this case, the horizontal asymptote is going to be y equals 0. So now we found the asymptotes, no vertical asymptote, but we're going to have a horizontal asymptote of y equals 0. Now, let's deal with the intercepts. Intercepts are easy. We're going to set x equals 0 and y equals 0, and we're going to solve. So, that's going to be for the y-intercept. We're going to set x equals 0. So let's do that. So, that's going to be y equals 5 times 0 over 0 squared plus 1. That's going to be 0 over 1, or 0 for our y-intercept. Then for the x-intercept, we're going to set y equals 0. So that's going to be 5x over x squared plus 1. And we know that the denominator here can just multiply up with the 0, and it's just going to vanish. So we're going to be left with 0 equals 5x, or x equals 0 for our x-intercept. As it turns out, the x and the y-intercept are the exact same points. They're going to pass through the origin. Now let's deal with the maximums and minimums. So this process is essentially the same basic process, except it gets a little more complicated because you have to use quotient rule. I simplified it a bit. I've just gone through and done the quotient rule already. If you are still a little bit stuck on that, I'm going to recommend you go back and consult 4.10, I believe it was. So, but otherwise, hopefully you're good with that, and we're going to continue on. Now, the other big difference between rational functions and polynomial functions is how we find our critical numbers. With polynomial functions, all we did was we set f prime of x equal to 0, which we're still going to do. But we also, think back, we said that critical numbers could also be spots where the derivative does not exist. So we'll come back to that bit a little bit later, but just keep that in the back of your mind. So let's start with f prime of x equals 0. Let's start with setting the denominator equal to 0. So 0 is equal to -5. Let's use this version up here just because it might be a little bit simpler. X squared minus 1 over x squared plus 1 squared. So in this case, now that we have it set equal to 0, the denominator will multiply up with 0, and it's going to vanish. So we're going to have 0 equals -5 times x squared minus 1. We can divide out the -5, and we're left with 0 equals x squared minus 1, or 1 equals x squared, or we square root it and we get x equals plus or minus 1. So that is the case where we have the derivative equal to 0. So those are critical points where we have a derivative equal to 0, our maximums and minimums. But we also know that with rational functions, we can have spots where we don't have a value, where we have a hole or a gap. So in this case, we're looking for any spots where the denominator is equal to 0. So what we're going to do is we're going to take the denominator from the second derivative, from the first derivative, this one here, and we're going to set it equal to 0. So 0 is equal to x squared plus 1 squared. We square root both sides. We get 0 equals x squared plus 1, or -1 equals x squared. Or we square root it, and we get plus or minus square root of -1 is equal to x. But in this case, because we know that that's not a real number, we don't have to worry about it. So not a real number, so we know we're not going to have a critical point. If it worked out to be a point there, it would mean that we have a non-differentiable point. We have a hole or a gap in our first derivative, which means that we could have a potential critical point that we'd have to put into our increase and decrease table, into our factor table. But since we don't, we just have positive and -1 to worry about. So we're going to break up our function into a few different regions, just like we did with polynomials. We'll start with everything to the left of -1, then between -1 and +1, then everything right of +1. And now that we have that, now we can start looking at the factors. So let's look at this one here, just because the factors are laid out really nicely. I showed both the non-factored version and the factored version, and this is why, because sometimes they'll help you in different ways. So use whatever one makes the most sense for you and easiest to work with. So let's write out those factors. So -5, x plus 1, x minus 1, and with the denominator, we're just going to list it like any other factor, even though it's a fraction, because the sign's not going to, the sign will work in the exact same way. We know that multiplying and dividing, while the operation is different, the rules are the same. If we multiply two negative numbers, they become a positive number. But if we divide two negative numbers, they become positive as well. So they work the same way. So we're going to look at the sign overall for each one. So let's go part by part. -5 is going to be always negative. For x plus 1, let's see, For the first region, that would be negative, and then it's going to switch over to positive. Just remember, pick a test number for each category. If you want to go column by column as well, that can work as well. But just to speed this up, let's go bit by bit. So just pick a test value. For the first column, it would be something less than -1, so -2 maybe. And then for the middle one, x equals 0 could work. As long as it's somewhere in that range, it'll work. So we could pick those test values and plug them in and try them out. And then for x squared plus 1 squared, we know that this is always going to be positive because when we square anything, it makes it always positive. So now we're going to multiply each column, all the signs, and see what happens. So we have 3 negatives for the first column, so 2 of them will cancel. We have 1 left over. So overall, the sign of our first derivative is going to be negative for the first bit. And then we have 2 negatives, so they cancel, and then we get positive. And then for the third, we just have the 1 negative, so it stays. Let me tidy up here a bit. Okay, so now let's take a look at our signs for our table. We said we have a negative derivative to start, so that means that we are going to decrease until we get to -1, and then we're going to increase to +1, and then decrease again. So that means that we're going to have a minimum at -1 and a maximum at +1, at x equals +1. So now we have a bit more information to help us out. Now let's try the same thing with inflection points. And again, just like polynomials, it works the exact same way. The only difference is that we have to use quotient rule, and we also have to check any other non-differentiable points where we get f double prime of x does not exist. So we have to check those two possibilities. So let's start with f prime of x is equal to 0. So we're going to set that derivative equal to 0. And again, I've done the calculation for you. Aren't I nice? So the denominator should just go away. It just multiplies up with 0, and we get 0 equals 10x, x squared minus 3. So now we know that we can use the zero factor rule and we can solve. So that's going to work out to be 0 equals x, or 0 equals 10x, but we know it's the same thing as x. Or 0 equals x squared minus 3, which when we rearrange that should work out to x equals positive or negative root 3. Or roughly positive or negative 2.2. And in this case, it's okay to use some decimals because we're going to need them for plotting anyways. It's kind of hard to plot root 3. So decimals are okay. So now, before we start making our factor table, let's just check to see if there's any spots that are going to be not differentiable. So f prime of x, we want to find the spots where it does not exist. So any spots where our denominator is equal to 0 or we divide by 0 are going to be spots that we have to check. So we're going to set our denominator for our second derivative equal to 0. So we're going to take the cube root of both sides. So cube root of 0 is 0. And then we get x squared plus 1, or x squared equals -1, or x equals positive or negative square root of -1. So there's not any real numbers there, so no asymptotes. No critical numbers, I should say. These aren't asymptotes because we're dealing with the second derivative, but they could be potential critical numbers. And again, if it were a real number that we found here, it could be a possible inflection point. Sometimes we can have an inflection point around an asymptote where we change from concave up to concave down, like, with 1 over x. We are concave down on one side and concave up on the other side. So actually, in this case, that could be another potential critical point. So we always have to check for that. So now that we have that, let's set up our factor table. And now we have 3 different potential inflection points that we have to think about here. So we could have anything to the right or to the left of negative root 3. We could have anything between negative root 3 and 0. We could have anything between 0 and root 3. And then anything to the right of root 3. And let's take a look at all of our factors. In this one, we had 10x, x squared minus 3, and then we had x squared plus 1 to the power of 3. So for 10x, the sign is just going to change with whatever x is. So if x is negative, it's going to be negative. So negative, negative, positive, positive. And then for x squared minus 3, just pick a test value for each category, and it should work out to positive, negative, negative, positive. And then for x squared plus 1 to the power of 3, let's see, x squared is always going to be positive. If we add 1, it's still going to be positives. And if we take it to the power of 3, it's still going to be positive. So we have positives across the board. So now examine the signs. So we have negative, and then 2 negatives make a positive, negative, positive. So we said that from the second derivative, we're determining our concavity. So if we have a negative second derivative, it means that we're concave down. I'm not going to put the arrows because that's a little confusing. That kind of means the same thing as decreasing. So concave down to concave up to concave down to concave up. So it means that every spot we're changing concavity. So now that we have all that information, now is where we get to start trying to plot all this information. So let's go up to the top again, and we're going to go bit by bit. So we said no vertical asymptotes, but we have a horizontal asymptote of y equals 0. So let's start by plotting that. And then, let's see, we have intercepts. We said that the intercepts, the x and the y, are going to be in the same place. It's right at the origin. So we can plot that. For the maximums and minimums, we said that we're going to have a maximum at positive and negative 1. But we also need to know the values there, so we can just calculate f of 1 and f of negative 1. And let's see, did I put that in my notes? I did not. Let me just calculate that real quick. So we're going to plug that into the original function. So that's going to be 5 over 1 plus 1 is going to be 5 over 2, or 2.5. And then we're going to have negative 5 over 2, so negative 2.5. So let's plot those points really quick. So we're going to make sure that we plot some numbers here. So 1, negative 1, 1, 2, 3, 4, 5. Just enough so we get the gist. And then we have 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5. So let's plot those points. We said positive 1 is going to be 2.5, and negative 1 is going to be negative 2.5. So now we're already starting to get some information. So think back to the maximum minimum points. We said that we're going to have that maximum and that minimum, and then we're going to be decreasing. We're going to be increasing, and then we're going to be decreasing. And then for the inflection points, we said that we could have, let's see, we said 1 at 0, 0, which we already plotted, and we could have 1 at root 3 and negative root 3, and those are going to be, let's see, my handy dandy calculator here, that's going to be root 3 divided by squared plus 1. That's going to be about 2.16 or negative 2.16 for the negative side. So let's plot those really quick. So something like this here and this here. And then we said that it's going to go on either side of that. It's going to go, we said concave down to concave up to concave down to concave up. So now the trick is just taking all of that and we're going to plot that into our graph. So we said we start along the asymptote and we're not going to pass over, so we just kind of go this way and we're going to be concave down and decreasing. And then at this point we switch to concave up. We're still decreasing. And then we get to negative 1, at which point we increase. And now we switch to concave down, as we mentioned below, or increasing. And now at this point, we switch to decreasing. We're still concave down. And then we're at the inflection point, in which case we switch to concave up. So our graph is going to look something like that. So I'm going to draw it once more, just so it's really clear here. In fact, maybe I'll just draw it with a big pen, just so we can really see it. And so that's pretty much the graph. That's all there is to it. So now that we got that, let's try one more. So same basic process. We're going to find the asymptotes, the intercepts, the maximum and minimum points, and the intervals of increase and decrease, and then find the inflection points and the concavity points. So let's start with the vertical asymptote. Vertical asymptote, we're just going to set the denominator equal to 0. And we're going to get x equals 4 as our vertical asymptote. Okay, next is horizontal and oblique asymptotes. So take a look. We said we're going to look at the degrees first. In this case, we have x squared over an x. We have 1 degree higher in the numerator. So we're going to have an oblique asymptote in this case. So you can use whatever method you like. If you like long division method or synthetic or the rectangle method, whatever method works best for you, go with that. But either way, I'm going to do the calculation really quickly. X minus 4 x squared minus 3x plus 0. And let's see, it's going to be, just to speed things up, just because hopefully you guys are okay with this, I'm going to just write it out really quickly. X squared So in this case, we have an asymptote, a slant asymptote around y equals x plus 1, which is our oblique or slant asymptote. So now we have our asymptotes. Let's find the intercepts. Let's start with the x-intercept, and we'll set y equals 0. So that's going to be 0 equals x squared minus 3x over x minus 4. So in this case, the denominator will multiply up with 0 and cancel, and we're left with 0 equals x squared minus 3x. Or you can factor that, it becomes x times x minus 3. So x is going to be 0 or 3. So we're going to have x-intercepts at 0 or 3. And then for the y-intercept, the same thing, except just set x equals 0. So y equals 0 squared minus 3 times 0 all over 0 minus 4. And that's going to work out to 0 for our y-intercept. So now that we got that, let's just start plotting in our data just as we go, just to make it easier this time. So we said we have an asymptote, a vertical asymptote around x equals 4. And I'll skip the big fat marker this time, and I'll just use this. Hopefully it's a bit easier to read. And then we have a slant asymptote around y equals x plus 1, which is just y equals x, but shifted up by 1. And then we have intercepts at 0 and 3 on the x-axis. And then 0 as our y-intercept. So we can already see it's starting to take a bit of shape, but let's gather a little more data before we start filling in this whole thing. So again, nice, Mr. Henderson did the derivative for you. So make sure you know how to do that. But all we're going to do is we're going to find all the spots where f prime of x is equal to 0 or f prime of x does not exist. So for f prime of x equals 0, we're going to set the derivative equals 0 equals x minus 6, x minus 2 over x minus 4 squared. So in this case, the denominator is going to multiply up. That goes away. And we're left with x equals 6 or x equals 2 as possible critical points. And then for the spots where f prime x does not exist, let's set the denominator equal to 0. Square root both sides, and we get x minus 4 or x equals 4. So in this case, now we have 2, 4, and 6 as our possible critical points. So we have to look around those. So let's start with x to the left of 2, between 2 and 4, between 4 and 6. And let's examine the sign and see what's going on. So break up our factors. So for our derivative, it was x minus 6, using this one here, x minus 2, and x minus 4 squared. So let's look at each section of this graph. Let's pick a test value. For the first one, for x is less than 2, let's pick x equals 0, and that's going to be negative, negative, positive. In fact, x minus 4 squared, because it's squared, it will always be positive, so we can just fill those in right away. Between 2 and 4, we can pick 3, so that's going to be negative. This one's going to be positive. And then let's see, for the next category, we could do x equals 5. So 5 minus 6 is going to be negative, positive, positive. And then for x is greater than 6, let's say x equals 7. So that's going to be positive, positive, positive. So let's look at the signs here. So we have the first category, x is less than 2. The negatives are going to cancel, and we'll be left with a positive, then a negative, then a negative, then a positive. So in this case, we are increasing, then decreasing, then decreasing, and then we're increasing. So in fact, in this case, we actually don't have a local maximum minimum point, but we're going to have a spot where it kind of levels off in the middle, or we might have an asymptote. In fact, right around that, in fact, remember that that was x equals 4 where that happens, and we know that's an asymptote, so that could be it. Sometimes when that happens, when we have two decreasing intervals around a critical point, it could look something like this, where we have just the slope of the tangent just kind of levels off. Sometimes that happens. It could look like that as well. But if it's an asymptote, then that's obviously what's going on there. So we're going to have a maximum. Then we're going to have the asymptote. I'm just going to abbreviate that as vertical asymptote. And then we're going to have a minimum at that point. And lastly, let's talk about the inflection points. So we said we need to find the spots where the second derivative is equal to 0 or it doesn't exist. And again, I've done the quotient rule for you. Luckily, this one simplifies very nicely. It becomes 8 over x minus 4 cubed. So that's pretty easy to do. So let's start with setting it equal to 0. 8 over x minus 4 cubed. The x minus 4 cubed will multiply up, and we get 0 equals 8, which we know doesn't make sense. So in this case, we don't actually have any solutions where x equals 0. So let's take a look, though, when it doesn't exist. So we're going to set the denominator equal to 0 this time. Square root it, and we get x minus 4, or 4 equals x. And again, we know it's that asymptote, it's at the asymptote point, so we can kind of examine what's going on to the left and right of the asymptote to help us out. So x is less than 4, x is greater than 4. So in this case, we know it's already going to be the vertical asymptote there, but we want to look more to see what the concavity is going to look like in each point. So we're going to have 8 x minus 4 cubed just from our second derivative. And for that, 8 is always going to be positive. But for x minus 4 cubed, for the first one, it's going to be positive, negative, and then we're going to be positive. So that means that for x is less than 4, we're going to be negative, or concave down. And then for x is greater than 4, we are going to be concave up, or positive. So now that we have that information, let's plug all that. Let's just kind of summarize that around our graph so we can put that all in. So we said we have a max around x equals 2. We're going to have a min at x equals 6. And then we're going to have, we're going to have increasing to decreasing, decreasing to increasing. Okay, and then we said for concavity, we said it's very simple. We're just going concave down to the left of the asymptote and concave up to the right. So let's see if we can put all that together. So for this one, we're going to let's start around the asymptote because that kind of makes sense. So we're kind of decreasing around the asymptote. So we have the intercept here, and we're just going to decrease down. And then on the other side, we're increasing. We're passing through the origin as our y-intercept. So something like this here. And in fact, we could find that maximum as well. It's actually just positive 1. So let's You just find that by plugging the 2 into the original function. And then we're going to start decreasing from the asymptote. So it's going to start the asymptote and come down again. And for this one, it's going to be 9. That's going to be our 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, I just found that using the original function. So we decrease from the asymptote, and then we're concave down, decreasing towards our minimum, and then we start increasing again. So we just confirm it's concave down to the left, concave up to the right. We're decreasing and increasing all the right intervals, and our minimum maximums are in the right places. So this is now fully sketched. So you now have all the tools to sketch with rational functions. And in fact, at this point, if you know how to differentiate a function, you can actually sketch it using the tools that we have learned here. So any function you come across now, as long as you can figure out all this information for it, you can sketch it. So hopefully that helps. It's one of those skills that takes a bit of practice. Make sure you do some practice, but I hope that this has been helpful. And next lesson, we will go right into optimization, which is the last portion of this unit. Thanks, guys. Take care.